YouTube always takes a hot second. Hey, excellent. Okay, well, it seems like we're recording here and everything is all ready for our Monsoon seminar for today. So I'd like to thank all of you for showing up this week for our Monsoon seminar on kind of the alternating schedules. And so I'd like to welcome our speaker for today, Mathias Vuille, who is a climate scientist in the Department of Atmospheric and Environmental Sciences at the University of Albany. He received his PhD from the University of Bern in Switzerland, and he teaches a variety of graduate and undergraduate courses on climate change, paleoclimate, and other major topics across environmental science. His research focuses on South American paleoclimate and climate change impacts in the tropical Andes. And he served in the past as a senior fellow for the US State Department's Program on Energy and Climate Partnerships in the Americas, as a contributing author to the Intergovernmental Panel on Climate Change, as an associate editor for the Geophysical Research Letters journal, as a member of the US National Committee for the International Union for Quaternary Research, so INQUA, and on the Science Leadership Council of the Mountain Research Initiative. And he's published to date over 140 research articles on climate change in South America. So without further ado, I'd like to welcome our speaker for today, and I'll turn it over to you. Thank you.
Thank you so much for the introduction, and thank you everyone for joining. Good morning, good afternoon, or good evening, depending on where you are located. It's a pleasure to be here and talk a little bit about our work in South America and as it relates to the past history of the South American monsoon. What I'm going to show you is really work over a number of years that we have done, and it involves a very large team. So I want to thank all my collaborators that have contributed to this work. I can't name them all by name, there are too many, but this was all work that has been done under the so-called PIRE Create framework. So I want to take a few minutes at the beginning to briefly explain who we are and what we do and why we do it before I start focusing on the actual monsoon. So the PIRE Create project, it's an acronym. PIRE stands for Partnerships in International Research and Education. And sorry, got to go back here one. These are large international projects that are funded by national research foundations in individual countries, with the idea that it should provide a framework to address global challenges that one country cannot solve alone, or also one discipline cannot solve alone. So challenges that require international collaboration and interdisciplinary teamwork. In our case, we're focusing on climate research in the Americas. So our project is called CREATE. You can see it here, Climate Research and Education in the Americas, using tree ring and cave sediment examples. It's a long acronym, but basically we're trying to better understand how climate in South America and North America has varied in the past. And we're using tree rings, cave sediments, speleothems, but also other proxies and models to do that. And our work is funded by NSF in the US and by the Sao Paulo research agency, FAPESP in Brazil. So we're a large group of scientists, faculty members, graduate students, postdocs, even undergraduate students from different universities and institutions in the US, in Brazil, and in Argentina. In the US, it's primarily us here at the University at Albany and Columbia University. In Brazil, it's the University of Sao Paulo and the University Federal Fluminense in Niterói, near Rio de Janeiro. And we're also working with the Argentinian Environmental Research Lab for Snow and Nivology in Mendoza, Yanigla, in Mendoza, Argentina. And this is a crazy diagram here. I don't want to bore you with this or look at all this in detail, but I just wanted to highlight that while we are doing research, this is really not the only thing this project is about. it's really important for us that we integrate students and early career scientists in all aspects of our program, all aspects of our research. So education is really, really important. And equally important is that we don't want to do research in a scientific bubble, but we think that many of our research results have relevance for policy and decision makers. So we're trying to provide also deliverables, translate our research through visualizations or other means into something that policy and decision makers can actually understand and also use, so that it has some policy relevance as well. But today I really want to focus just on this one box up here, and that is monsoon reconstruction. For the educational part, what we're doing or have been doing is we've been offering internships. So we're trying to send some of our students abroad to labs abroad so they can learn new tools. We've organized summer schools where students from different countries can meet with different backgrounds, different languages, different culture. So there's also really an experience that students meet one another and learn from one another. Unfortunately, we cannot bring all of our students with us. So in the US, in New York, we have also been organizing smaller events on like 3 to 4 days, weekends, where we engage undergraduate students across the SUNY system. So SUNY is the State University of New York system. It's one of the largest university systems in the world. Over 60 campuses, about 400,000 students, many of them first-generation students or from underrepresented groups. So we're trying to engage them in science and technologies and get them excited about our work as well. For the last 2 years, this obviously has been very difficult because of the COVID pandemic. So we have basically been forced to go online. So we've had organized webinar series instead to keep our students engaged. Some of those were in Spanish, so we also could continue to collaborate with our colleagues in South America. So this is sort of a glimpse of what the project is all about and what we're doing. So now, why are we looking at the South American monsoon, or why does it matter how the monsoon has varied in the past? I think for this audience here, this is probably an obvious question. We're scientists, we're curious, we want to know how things have changed over the past. But it's also important, I think, to recognize that this work is relevant for many social, economic aspects as well. In particular, in South America, the monsoon is really important because it provides water for many different uses, whether it's for agriculture, industrial use, hydropower production, and so forth. Monsoons, of course, also vary. We can have monsoon failure. We can have a very intense monsoon season. It can lead to droughts or floods. So it can provide an environmental hazard. And fundamentally, we are now in a situation where monsoon characteristics are starting to change because of the change in radiative forcing, because of our release of greenhouse gases. And in South America in particular, there's a lot of uncertainty how the monsoon might change. And it's really important to have this longer term perspective to really understand what sort of the natural envelope of variability is and when we might actually emerge outside of this past envelope that has dominated the monsoon in the past. So for those of you who are not so familiar with South American climate, just a very brief overview. This is just sort of a cartoon that I borrowed from my colleague, René Garot, that shows the main ingredients of South American climate, at least at the lower level, during the austral summer when this monsoon develops. Most of the moisture for the South American monsoon is brought in through easterly winds from the tropical Atlantic. The main conduit, moisture conduit for this is the intertropical convergence zone that moves further south at that time of the year. You then have moisture convergence, and associated with the stronger insolation during the austral summer, you create convective conditions, uplift and rainout and monsoon precipitation. The moisture flux then, once it hits the Andes, is diverted. A lot of the moisture is transported south along the Andes, along what's called the Andean low-level jet, and then transported southward towards the La Plata Basin region, where you have another convective band that forms here, the so-called South Atlantic Convergence Zone. Over the ocean, of course, we have large-scale subsidence, primarily associated with the anticyclones over the Southeast Pacific and the South Atlantic. If we look at this a little bit closer, you can see that the monsoon really is a Southern Hemisphere summer phenomenon. The top two panels here in green show you the precipitation amount in January, and January is really sort of the core season of the monsoon. The monsoon starts to develop around maybe October. It hits a mature phase in December, January, maybe February, and then April, March, we see the demise of the monsoon. And you can see that the monsoon here protrudes far south over the continent. It's clearly distinct from the intertropical convergence zone that you see over the Pacific and the Atlantic that resides north of the equator, even during the austral summer. Over here on the right, we're still looking at January. It's the same precipitation field, but it now shows the upper tropospheric circulation. And there's a couple of things that I want to highlight here that are quite important that I'll come back to later in my presentation. You can see that we have sort of an upper tropospheric waveguide here. We have an anticyclone that forms here. That's the Bolivian high. And over the northeast and the adjacent tropical Atlantic, we have an upper tropospheric cyclone, a low pressure system, the so-called Nordeste low. These two features are associated, they form as a response of latent heat that is being released over the Amazon basin because of convection. So when you have convection and then condensation, that releases latent heat that excites the upper troposphere and leads to this waveguide. So this is a very diagnostic feature of the South American monsoon. You can see if we look down here in July, this has completely disappeared and is replaced by zonal flow. So the monsoon is really a seasonal phenomenon. It develops only during the Southern Hemisphere summer, while during the winter months it is gone, and convection is limited to the northernmost part of the continent, and this dynamically really is tied actually to the North American monsoon. So how do we now define the monsoon if we want to use this in an isotopic paleoclimatic framework? Well, for us, it's really important to understand where the majority or a large fraction of the monsoon falls during the monsoon season. Because if we look at isotopic proxies, they incorporate the isotopes through the rain that falls at the site where the proxy is located. So they're all only recording climate at the time when it's raining or snowing. During the dry season, they aren't really recording anything. So we really want to sample proxies only in those regions where the majority of the snow or rain falls during the monsoon season. And that's highlighted here on the left in these orange and pink colors. The scale is here below. This shows you the fraction of the total annual precipitation that falls during the monsoon season, December, January, and February. So this really is our monsoon belt. And you can see that during the austral winter, June, July, August, we really don't have a monsoon over the tropical continent. Now, since we're using isotopes, very briefly, the framework in which we interpret this, I assume you're mostly familiar with the delta notation. We're looking at oxygen isotopes in calcite or in ice. So we're looking at the ratio of the heavier to the lighter isotopes, oxygen 18 to oxygen 16 in a sample. We're comparing this to a standard. In this case, the standard is SMO, so the standard mean ocean water. And we're then standardizing it. We're dividing by the standard because this is a very small number. We multiply by 1,000 and then express it as per mil. So in essence, and that's shown here in this cartoon, we interpret the isotopic composition of precipitation as recording fractionation process along the transport history. You can think of this cartoon here as a cross section across the tropical Atlantic and tropical South America. So you have the Amazon basin here, and then you have the Andes further to the west. The moisture source for all of this precipitation is the Atlantic. So water evaporates here over the Atlantic, and as it evaporates, because oxygen 18 is isotopically heavier, it will preferentially reside in the liquid phase, while the lighter isotope oxygen 16 will preferentially evaporate and accumulate, if you will, in the water vapor in the atmosphere, in the cloud here. This means that the isotopic composition of the water vapor is depleted in the heavy isotopes, so it starts to become more negative with respect to the ocean water. This water vapor is then transported inland by the trade winds. You have moisture convergence, uplift, and condensation. When you have condensation, you again have fractionation. The heavier isotopes will preferentially rain out, while the lighter isotope oxygen 16 will preferentially reside in the water vapor, meaning that the water vapor becomes even more negative. So in essence, as an air mass is transported across the continent, the more condensation and rainout occur, the more negative the remaining water vapor in the atmosphere will be. And ultimately, we can analyze the isotopic composition of the rain that falls, because it might be incorporated in lake calcite in a lake, or in calcite in a speleothem in a cave, or it might be incorporated as snow in an ice core in the Andes. But essentially, we, in this Rayleigh distillation framework, we interpret the values that we're recording in these proxies as basically recording the degree of rainout and therefore the monsoon intensity, the convective intensity upstream. So how do we define monsoon intensity to basically test whether this framework works or not? Well, we can basically look at convection during the monsoon season over South America. And that's shown here in these gray colors. This is OLR, outgoing radiation, long wave radiation. So it's basically a proxy for convective activity. We can use a very, very simple index where we basically just draw a box around this core convective region and look at how much rain falls in this box during the monsoon season and use this as an index. We can then take this index, the box is plotted here again over in this figure on the right, and compare this index through time with the isotopic composition at different locations across South America. Everywhere where you have one of these small blue boxes, this is a location where we monitor the isotopic composition in precipitation. This is done by the International Atomic Energy Agency, IAEA, through their global network of isotopes and precipitation, GNIP. These colors here indicate the correlation of the isotopic composition at each one of these locations with the precipitation during the monsoon season in this black box. The scale is down here, and you can see blue colors indicate negative correlations. So what this means is the more rain falls in this black box during the monsoon season, the more negative the isotopic composition is at all of these locations. Wherever you have a white cross, it means that the correlation is actually significant. So this suggests that the precipitation intensity in this box in the monsoon region does actually significantly influence the isotopic composition throughout much of the region, even outside of the box itself. We can test this exact concept using an isotope-enabled model. This is an old model from early work that we did, an atmospheric model, but it is isotope-enabled. And it shows the same concept. So wherever you have blue colors here, it means there you have a significant negative correlation between the isotopic composition with the precipitation in this white box in the core monsoon region. And this suggests that we have a significant negative correlation far outside the box in very distal locations. So for example, if you look at the isotopic composition in southeastern Brazil, it carries a memory of the degree of rainout that occurred far upstream over the core monsoon region. We can now apply this concept to proxies going back in time. And you can see there are different sites here that are labeled A through E. And over here now, we have time series reconstruction of the isotopic composition at these locations from A on top, that is Lake Pumacocha, lake in the Peruvian Andes, all the way down to E, Huagapo Cave, a cave also in the Peruvian Andes. And these records go back 2,000 years. So the present is over on the right where it says 2000, and we go back here in time about 2,000 years. And there is sort of three periods that are highlighted here by the colored vertical shading. The first here, MCA, about 1,000 years ago. This is what we refer to as the medieval climate anomaly. Then you have this green period here from about maybe 14 to 1800 common area, LIA, that is the Little Ice Age. And then the last 100, 115 years, named here CWP, the current warm period. We highlighted these three periods because these are three periods where many of these records show clear departures from the mean state. You can see, for example, during the medieval climate anomaly that several of these records indicate slight positive departures, more enriched values, and that would, using our framework, suggest a weakened monsoon. You can see during the Little Ice Age, most of these records show depleted values, more negative values, indicating a strengthening of the monsoon. And then over the last 100, 150 years, you can see that many of these records are now trending upwards again, suggesting a weakening of the monsoon over the last 100, 150 years or so. Now, these are just a few records. And the question is, what happened here during the last 1,000 years or so that led to these changes? And I want to focus in particular on this Little Ice Age period. And I want to use just one record here. That is Lake Pumacocha, a lake in the Peruvian Andes that has varved sediments that contain calcite, where we can measure the oxygen 18. This is a record that was produced by my colleague Broxton Bird at University of Pittsburgh for his PhD. And this lake record is plotted in gray, and plotted on top in green here is a reconstruction of Northern Hemisphere temperature. And you can see that these two records are almost one-to-one plot on top of one another, at least on sort of the century timescale. Even though they're recording very different things, the gray record records the strength of the South American monsoon. The green records records Northern Hemisphere temperature. So what we think happened here is that during the Little Ice Age, as we know, we had a change in the radiative forcing, a reduction in the radiative forcing because primarily of enhanced volcanic forcing, but also a reduction on solar irradiance. This led to a cooling in the Northern Hemisphere. And this cooling in the Northern Hemisphere led to a change in the meridional SST gradient in the Atlantic and a southward displacement of the intertropical convergence zone, shown here, for example, by the titanium input into the Cariaco Basin. suggesting drier conditions here over northernmost South America and a southward displacement of the ITCZ. We can also see this in sea surface temperature reconstructions of the North Atlantic that are shown here in the record D. More recently, we have tried to expand this concept a little bit, and this is work that was published just earlier this year by my colleague Byron Steinman at the University of Minnesota. By performing a EOF analysis, a Monte Carlo EOF analysis, using records now, not just from the South American monsoon region, but also north of the equator. And if we perform such an EOF analysis using highly smoothed filtered records, only looking at sort of the centennial timescale variability, you can see this clear change over the last millennium in the first principal component. And if we do this same analysis separately for records south of the equator and north of the equator, what we get are these two time series here, principal components shown in red for north of the equator and in blue for south of the equator. Now note that the principal component for south of the equator is multiplied by -1. They plot almost on top of each other, but in reality, they're actually mirror images of one another. They're anti-phased, as you can see by the very, very high negative correlation between the two. In other words, what this means is over the last millennium, when it was wet north of the equator in the neotropics, it was dry to the south and vice versa. And that's a clear indication that over the last millennium, we had this anti-phasing, and that this is the most likely explanation for this is a shift in the intertropical convergence zone. It's also consistent if we look at how the SST gradient in the Atlantic has changed, that shows this exact same behavior. And we can see this also over the last millennium in the EOF, the second EOF of sea surface temperature in the Atlantic. If we use a model, this is based on CESM, the Community Earth System Model Ensemble, or if we use a proxy-based SST reconstruction. In both cases, you can see this clear dipole in the sea surface temperatures, showing that over the last millennium in this mode, the two basins north and south of the equator were antiphased with one another. So a few years ago, Leandro Campos, PhD student at the time at the University of Sao Paulo, took this one step further to look at how the isotopic records that we have over South America have behaved over the last millennium using a similar EOF decomposition. And what's shown here is basically the first principal component and how it has behaved over the last roughly 1400 years, going back to 600 common area. And again, you can see this clear departure from the mean state during the Little Ice Age. Plotted over here on the right, just in a very qualitative sense, are the departures of the oxygen 18 of the different records that we have during this period. It is labeled here E1. This E1 period basically encompasses the Little Ice Age. And you can see that most records indeed show much more negative oxygen isotopic values, shown here in blue. But there are a couple over the Northeast that show the opposite behavior. And this again suggests that in South America, we have this dipole in the isotopic composition during the Little Ice Age that is related to this Bolivian high Nordeste low system. This hypothesis was tested and taken a step forward more recently by work done by Rebecca Orison, one of my graduate students. She basically repeated this analysis, but she used a denser network, more records, And she then also, as I'll show you in a minute, used isotope-enabled climate models to better understand the dynamics here. But wherever you have a cross here, we have a speleothem records, a high-resolution records that covers the last millennium. She also used the Pumarcocha record, shown here by the red circle, and an ice core that I'll talk a little bit more about in a minute, the Calcaya ice cap ice core record in Peru. So she used a similar EUF decomposition, and her leading mode looks very, very similar to the one that I showed you before, shown here. Again, clearly showing this antiphasing between the core monsoon region in the central Amazon, the Andes, and southeastern Brazil, and the antiphasing then over the northeastern region. And this is consistent, again, with this framework that if you intensify the monsoon, you strengthen the Bolivian high, you have more convective activity in this region. This uplift is balanced by subsidence over the northeast and an intensification of the Nordeste low that would lead to more enriched values over this northeastern region. We actually published a paper on this framework a long time ago, led by my colleague Francisco Cruz. This was applied more to orbital timescales, in particular for the mid-Holocene, but it's basically the same idea that in South America, we also have a zonally overturning circulation driven by convective activity over the Amazon basin that affects the upward motion over the core monsoon region, which is then balanced in the strength of the subsidence over the northeast. And that leads to this dipole between wet and dry conditions that are out of phase over the two regions. So we actually also see this during these two key periods. So plotted here is a composite analysis, plotting the isotopic composition in the different sites in our proxy network during the medieval climate anomaly on top and the Little Ice Age below. And you can see in particular for the Little Ice Age, clearly that we have this dipole, more negative values shown in green over most of the monsoon region, but over the northeast, we have this antiphased behavior. The shading in the background is the result from an ensemble of isotope-enabled climate models from CESM. And you can see that the background shading basically matches what we're seeing in the proxy. So the model actually can reproduce this dipole quite well. The only problem is that if you look over here, the model and the proxies have different scaling. So one scale here is for the proxies and the other one is for the model. And if you look at the values, you can see that the model, yes, it gets the spatial pattern right, but the amplitude is underestimated by roughly a factor of 4 to 5. So what I've shown you so far gives us sort of the broad scale aspects of how the monsoon has varied and how we can reconstruct that in an isotopic framework. But I also think it's really important to have a sense or sort of a mechanistic understanding of how the isotopes are actually incorporated into these proxies. And our Brazilian colleagues have done a wonderful job of doing that in their network of caves across the monsoon region, installing monitoring networks so that we really have a good understanding that what we're measuring, for example, in the calcite of speleothems is consistent with what is deposited today in the fresh calcite, or what we're measuring in the drip water, or even in the rainwater isotopic composition outside of the cave. I want to show you another example where we've tried to do something similar, and this is related to isotopes in ice. So we're going to Peru here to the Calcaya ice cap. This is the largest ice cap that we have in the tropics. It's quite famous because my colleague Lonnie Thompson already in the 1980s went up here to drill an ice core. You can actually see him here with a piece of an ice core, although this is a photo I took during a different expedition in Bolivia on Sajama. But Quelcaya is unique because it really has this clear delineation of annual accumulation that you can see here in this photo over on the right, because it is in the monsoon region. It snows during the monsoon season. Then you have a fairly long dry season with no accumulation, but deposition of dust. And that leads to a clear sort of annual layering. So we can count layers similar to a tree ring. We have been monitoring the climatic conditions, snowfall, the isotopic composition of snowfall on Quelcaya for a long time. And this monitoring really was led by my colleague Doug Hardy from the University of Massachusetts. We installed a weather station up here in 2004 on the summit of the ice cap. We've been monitoring snowfall and the isotopic composition here for a long period of time since 2004. And I just want to show you a couple of interesting results here. Here is one example. This graph shows you the annual snowfall, the annual accumulation on the ice cap. So each one of these colored lines is a different year. And we're looking on the y-axis here, just as the height change, so the snowfall amount on the ice cap. So you can see it usually starts to snow here at the beginning of the monsoon season around November, early December. And then we have fairly steady accumulation until about March, early April. And that's when the monsoon season ends. That's the monsoon demise. And then you can see during the rest of the dry season, we actually have a slight lowering of the snow height. This is due to settling of the snowpack, a little bit of wind scour, but also some sublimation that's going on here. And I just want to point out one line here, and that's this thick red line that you're seeing here, that it shows a very unusual accumulation history. Normally, we get about 2 to 2.5 meters of snow on Quelcaya each year. In that particular year, we got only about 60 centimeters of snow. This was the year 2015-2016, a very, very strong El Nino year. So you can see the impact here that El Nino has that tends to lead to drought in this part of the world. So in order to really link isotopes with climate, we can't just measure the climatic condition. We also need to sample the snow, of course. For the longer record, we have the ice core, but for the most recent years, this requires digging snow pits every year and taking samples that you then bring back home and analyze. And because we have hourly measurements of the weather, we know exactly when this snow fell, so we can align the isotopic composition of each individual sample to very specific local conditions, but also to very specific atmospheric circulation. This is just a picture of how you have to be sometimes a little bit creative if you want to bring samples home in frozen state. You have to store them somewhere until you can actually fly back home. For example, this can just be in a small freezer in a local grocery store. Now, it's also important to make sure that what we're measuring on Quelcaya, on this ice cap, is really related to the larger monsoon circulation. So if it's snowing on Quelcaya, how do we know that this is not just a local small scale event that has nothing to do with a larger scale circulation? So this is analysis. This is work led by a former postdoc of mine, John Hurley, who exactly looked at how the monsoon circulation ties in with the local snowfall on the Quelcaya ice cap. And it's a little bit hard to see, but these two panels, these are actually maps of South America. I hope you can see this thin white line here actually shows you the outlines of the South American continent. Quelcaya is located where you have this pink diamond. And then in blue colors, this is the precipitation amount in millimeters per day. And what we're looking at here are the 90th percentile of the most heavy snowfall events on the Calcaya ice cap. The other figure over on the right is the 60th percentile, so a relaxed criterion, but still heavy snowfall events. So basically what these two maps show you is that when it's snowing very, very hard on Calcaya, it's actually also heavily raining over the entire, or at least the central and western Amazon basin, okay? So these are not isolated events, but snowfall on Calcaya is tied in with large-scale monsoon rainfall over the Amazon basin. So to understand how the isotopic composition varies in the snow and the ice on Calcaya and how it relates to upstream monsoon circulation, John Hurley built a simple so-called isotopic forward model to sort of basically create a synthetic ice core, if you will, to simulate the isotopic variability in the ice. And I quickly want to walk you through this. It's fairly straightforward. This model works on a daily time step. So you first have to decide for each day, is it actually snowing on Calcaya, yes or no? So let's assume it is snowing. If that's the case, we need to know by how much it is snowing. So how much does the snow height change? We need to know the temperature profile of the along the adiabatic along which the air mass is lifted up from the Amazon basin up to the Andes to Calcaya. We also need to know the initial isotopic composition of the water vapor over the Amazon basin before it is starting to be lifted up. If we know this using simple Rayleigh fractionation process, we can calculate the isotopic composition of the snow that is then falling on the Calcaya ice cap. If it is not snowing, well, then we actually have slight ablation. So we have a slight reduction in the snowpack, the snow height, but sublimation also occurs, and that actually leads to a slight enrichment of the surface snow layer because sublimation leads to a preferential removal of the lighter isotopes. So we see a slight enrichment, and that also is accounted for here in the model. So that basically every day gives us an adjustment in the snow height and in the isotopic composition. So we can now run this model over a period of time where we have good data. We did this over a period of time from 2003 through 2016 on a daily time step. And the biggest variability that we see in the ice on Calcaya, at least in the current record, is tied to ENSO. What is shown here is the distribution in the observed ice core record over the last 15 years. And you can see that during La Nina years, we tend to have much more negative isotopic composition. During El Nino, it tends to be much more enriched. And there's been a lot of discussion, a lot has been written as to why that is and what the causes are. So we tried to investigate that with our model. And the first thing we had to do is to see, well, can our model actually replicate this bimodal distribution? So here you see the exact same thing, except this is now simulated by our forward model. You can see the model, it has some problems with really reproducing the variance, but overall it does a decent job. It clearly separates the more negative values during La Nina compared to the more enriched values during El Nino. It provides the same bimodal distribution. So the question now is, well, what is causing this? Well, because we now have a model, we can start to dig in and analyze this. And there's basically three sort of hypotheses that have been put forward. One, it has been argued, well, it's simply because of an amount effect, because El Nino tends to lead to dry conditions in this part of the world. So when it rains or snows more on Calcaya, we get more negative values. It's a reflection of the increased snowfall. Others have argued, no, it's a temperature signal. We know during El Nino, it's much warmer. And this is reflected in the isotopic composition. It's a temperature signal. And then some have argued, well, no, it's actually related to the upstream changes in the monsoon, because we know that El Nino, through a perturbation of the Walker circulation, leads to subsidence over the Amazon basin, less convective activity, therefore less rainout, therefore more enriched isotopes. Well, we can test all of this by running our model and each time keeping one of these factors varying and the other two we keep constant. So we're only allowing one variable to vary at a time. So shown here are now the results if we do this. First, we run the full model. The red bar shows you the enriched values during El Nino. The blue bar shows you the more negative, more depleted values during La Nina. Now let's run our model and we only vary the snowfall amount. If we do that, you can see we get a response in the right direction. The orange is the El Nino response. Blue is the La Nina response. It goes in the right direction, but it's much too weak to really explain what we see in the observations. If we just allow temperature to vary, we don't get this right at all. Actually, the signal goes in the wrong direction. And now we're only allowing the isotopic composition of the initial water vapor that is then brought up to the Andes to vary. And now you can see we actually get this signal right. And this is a pretty powerful indication that what we're measuring on Quelccaya in the stable isotopes really is not primarily a signal of the local climate, but again, it is recording the transport history across the Amazon basin and the degree of rainout upstream associated with convective intensity of the monsoon. So it's consistent with the framework that we have applied and interpreted throughout our proxy network. Here is just a different way of visualizing this. What you see here is just the observed Quelccaya oxygen isotopic record regressed against sea surface temperature and outgoing long-wave radiation. You can clearly see the ENSO signal here, the ENSO tongue in the Pacific. If we take our simulated record, where we only allow snowfall amount to vary, you can see we get nothing similar. If we only allow temperature to vary, again, we don't get the signal right. But if we only allow the initial water vapor isotopic composition to vary, we actually get a signal that looks very similar to the observed record. So I've talked for a long time. I will end here, but I just wanted to pull in a plug. If you're interested in other things that we're doing with this PyroCreate project, feel free to contact me. You can also take a look at our website where we have a lot more information. We also have a YouTube channel with webinars and interviews and videos of many of our activities. We have a lot of interactive online tools where our data can be accessed. For example, we have an online interactive globe with a 2,000-year climate reconstruction of temperature and hydroclimate. This is a data assimilation project led by collaborators at Columbia University. So a lot more information is available on what we're doing in this project. So again, I want to thank you for joining me this morning. And if you have any questions, I'm happy to answer them. Thank you very much.
Thank you so much for your wonderful talk and sharing what you and your students and your collaborators have done. It's a ton of work and it's very, very cool. And a lot of excellent resources for us to explore them, probably just right after this talk. So I can already see that there is a question in the chat from Rohan. Rohan, would you like to read out your question or should I read it out for you? I'll give them a moment to respond. Okay, so I'll read it out. So Rohan writes, one of your slides, you've shown that there is some anti-phase relation over South America, which you inferred by a model where the anticyclonic air mixes up with cyclonic air parcel. So my question is, if it happens, then condensation of extra water vapor would take place. So local rainfall would increase again and would contribute to more negative oxygen isotope.
Yeah, thank you for the question. It's an excellent question. Maybe I didn't explain this all quite that well, but I'll try to explain it again. So the water vapor, of course, is transported in at low level. That's where we have the moist air with a warmer temperature. And then when convection occurs or condensation over the core region of the monsoon, the most of the water vapor condenses and rains out. So the remaining air that is up aloft is actually very dry. That is then balanced by subsidence over northeastern Brazil. So this is very dry air, and as it subsides, it actually warms up and dries out even more. So it's not actually water vapor that is transported through this zonal circulation. It's just air, dry air. So the subsidence actually just inhibits local convection over northeastern Brazil and therefore leads to drier conditions there. So this is not a loop of water vapor. I hope maybe this helps answer the question. But in essence, it is, you can think of it as when you have uplift somewhere and you bring air masses up, this has to be balanced somewhere by subsidence. And it is well known that, in fact, subtropical anticyclones that we have over the oceans are a result of monsoon convection. And the monsoon convection over South America, but also over Africa, actually strengthens this anticyclone through subsidence, in particular along its equatorward side.
Okay. If you have any further follow-up, Rohan, just feel free to raise your hand or turn on your video or write a follow-up question. I see that there's a raised hand immediately from Cristiano here in the gallery. So Cristiano, would you like to ask your question?
Yes. Can you hear me this way?
Yes.
I can hear you. Yes. Thanks.
Okay. Yeah, thank you very much for the fantastic talk, Mathias. Thanks a lot. You showed in this very elegant way how the Quelcaia delta 18O signal is affected by changes over the Amazon. Would you say that downstream sites in the pathway of the, say, monsoon low-level circulation over South America, more specifically southeastern Brazil, for example, or southern Brazil, that those sites would also be affected and in a similar way as Quelcaia is?
Yes, I think so. I mean, I think it depends a little bit on the location, and you know this as well as I do. So some of the sites that we used, for example, are Crystal Cave, also Botuverá. The problem comes when you go to locations where you, of course, no longer have just dominant monsoon precipitation. Quelcaia is almost exclusively sourced by the monsoon. It has a very, very long dry season. But in southeastern Brazil, you know this better than me, you then also get some winter precipitation, and that is Atlantic sourced from is a different source. It's not monsoon precipitation. So when you start to mix those signals, it gets a bit more complicated. But at the same time, it can also get very exciting because maybe on long orbital timescale, like the long Botuverá record, which seemed to suggest that you can actually reconstruct how the mixing of more monsoon versus more maybe extratropical precipitation changes over time. I don't know if that answers your question or if that's what you were expecting to hear.
No, that answers my question. If I still have the chance to ask another question, is that okay? If I
Yes, yeah, go ahead.
Yeah. So would you you showed say details about the last 2,000 years and little ice age, medieval climate anomaly. Would you now say, I don't want to put words in your mouth, but would you say that we could export this notion or this rationale to millennial scale changes of the last glacial?
Yeah, don't put words in my mouth. I think it gets a little bit more complicated because, of course, now you have boundary conditions that are very different, right? As you know, and you as an oceanographer know this better than me, but with the different boundary conditions, with ice sheets changing the SSTs, I think it does make things quite a bit more complex. I think that some of the work that I've shown, and I think we maybe have to separate out here a little bit the spatial and the temporal aspect. When we do this decomposition into main modes, what we basically get, we get a spatial pattern, and then we get a time series that tells us how this spatial pattern has varied through time, right? I think the spatial aspect of this is quite stable, because I think some of this is inherent to South America because of the shape of the continent, because of the topography. And as far, to some extent, even the land surface condition, at least if you go as far back as, say, the large-scale vegetation doesn't change, because over land, of course, the monsoon feeds off and is affected by the vegetation, soil moisture, and so forth. So I think as long as you keep those things constant, I think these main modes are quite stable spatially, but of course not in time. The temporal aspect of this very much depends on the external forcing, and that is very different, of course, during the last glacial. So that's about as far out on a limb as I am willing to go, if that helps you. But sure. Yeah, we can continue, and I know we will continue this discussion. And of course, I need to add, I provided a terrestrial perspective here, and what your work that you're doing is very complementary in the sense that you provide an oceanic perspective to this, and of course, you also provide the terrestrial perspective in terms of what through river runoff, through terrigenous input, what ends up in the ocean, that is in some sense a terrestrial signal too. So I've provided just a small glimpse into a much more complex problem, and your work has and will continue to contribute a lot to that as well.
Well, yeah, thank you a lot. That helped a lot. Yes, thanks.
I have a very quick question before we should probably let you go. So I was really impressed with kind of the coherence in a lot of your proxy records, especially at this time scale. And I guess except for maybe one case, but this could just be of maybe me mixing up what I was reading on one of your prior slides. So in your records, do you find any evidence or issues with lag time actually in your proxies, and how they're recording essentially either changes in the ITCZ or the monsoon? Because considering that you're looking at, tree rings, cave records, lake records, and potentially different materials and species and all of those, it's really impressive that the signal would be so coherent among all of them. Mm-hmm. And just to, again, follow up on what I was saying, this is a bit of a long-winded ramble, sorry.
No, it's a very good question.
And, sorry, just in the reference to the slide that I was thinking about was the one that you showed for Lake Pumacocha and the Cariaco Basin, showing the trends with the little ice age and the medieval climate anomaly, mm-hmm. as well as with your Delta 14C record, which, if I recall, the Delta 14C record was a little different.
Yeah, that record is not ours, right? It's just one record. It's Delta 14C, and I think the other one was maybe a beryllium record. It was related to the solar irradiance changes. So this is a record from Bard et al, and the other one may have been Steinhill, but I can't remember. So this was just to show the comparisons with the solar irradiance and the change in the radiative forcing to the Little Ice Age. So the general answer is, the records that I showed are all reasonably high resolution. We have a few that are annually resolved. Pumacocha, the lake record, is one of those because it has annual varves. Quelcaya is one. Most of the other records, the speleothem records that I showed, they are subdecadally resolved. But of course, these are uranium thorium dated. They have a small h uncertainty, right? And that's why we're using this Monte Carlo EOF approach. So when we calculate the principal component, we don't get one principal component, we get 1,000, right? And we're sort of showing the median of them. So there of course is some temporal uncertainty here. As far as the lags are concerned, I think that, you know, the atmospheric response to an oceanic forcing is very quick. There is not a long lag here. The atmosphere in that sense is not like the ocean. It doesn't have a very long memory. The lag comes in more with some of the proxies. So if you have a speleothem, for example, and you have an aquifer on top and you have mixing and it takes a while until the rainwater actually makes it to the cave, then there is, for example, there is a lag. But in most of the caves where my Brazilian colleagues are working, that is not really the case. They know this because of the monitoring when you compare the drip water isotopes with the water isotopes of the rain above. So that's not really that much of a concern, but we are not analyzing really the interannual variability. I think we don't have the capacity to do that at this point. So in the paper that my student Rebecca published just this year, one reviewer asked about ENSO. And we had to say, well, that's probably a really interesting question, but ENSO is really strong on the interannual timescale. And we don't really have, when we combine 12 records, the resolution to say much about that. We can do it on Quelcaya, as I showed you, because there we really have an annually dated clear signal. Sorry for the long answer.
No. I think that was really good because I think it showcases the resolution of your record, where especially for those of us working on longer timescales, that's an incredible resolution to be working at. And you can really definitively say if you have lag or not, which I think is quite fun.
And my really all the credit here goes to my Brazilian colleagues, Francisco Cruz, Nicolas Triquis, Valdir Novello, Giselle. You know, all of them who have been doing this work for so many years. I'm just fortunate to be able to collaborate with them. But we here on the US side are really doing more the modeling and helping with the statistical and dynamical interpretation. But all the hard work that goes into producing these records, I did not show that, but that is all done by our Brazilian friends. So.
Well, I want to thank you again for such a wonderful talk and sharing the work again of yourself and your colleagues and what you've done together and what you've been able to do even since COVID hindered a lot of your international collaboration, especially with such a large group of people. So please put your digital hands or your physical hands together for our speaker for today. And before all of you run off, I just want to remind you that we do have another seminar next week on the alternative schedule, Schedule B. So it's more in tune with East Asian, South Asian, and Australasian time zones. And so our speaker for next week on the 23rd will be Alex Webb, speaking about the Himalayas over really long time scales and the development of the monsoon there. So thank you again so much for your talk. And I hope that everybody here has a really good morning, afternoon, or evening, depending wherever you are. So with that, have a good rest of your day, everybody. Thank you.
Thank you. Bye-bye.